Okay, everyone, we're going to start. Luckily, there's the video for those who are late. So last week we saw things about the TCP-IP architecture and the layered architecture, and I hope everything's going fine in the lab so that you can understand better all I said last week. And if you have questions, don't hesitate to ask me. If I have time by the end of the class, I will do something to review a bit the most important things that I think were maybe unclear. That's what I understood from the questions during the lab session on Friday. So today we're going to focus on the next part, which is on the programmer's view of the transport layer. So I said that the transport layer handles a lot of things for the communication process, and today we're going to see how can we actually program this interface. How can we program this layer from a programmer who would build an application, for instance. So the TCP layer, the transport layer uses a library, typically called the socket library, and which has functions. So just like when you write a C program or Python code, sometimes you don't want to rewrite functions that already exist, so you can just call a library and reuse these functions. This is exactly the same here. And we use this socket library for both UDP and TCP. So let's see step by step what happens. So for the UDP process, the UDP protocol, we have, in both cases, UDP or TCP, we have a toy example where a client and a server want to communicate. So in this very simple example, the client will send a request to the server. So first of all, what needs to happen on both sides is that they need to call this socket function, which creates a socket and returns a number. It's a file descriptor, and it will basically create some kind of a buffer that will be used for this application, so that if you need to send information or read information or receive information, you can store it in this particular buffer that will be attributed to your application. And because sometimes you cannot read right away all the messages you receive. So it's stopped there, and the socket function will make sure that you have this buffer. The bind function will link this buffer to the local port number that you have on your computer. So if you receive messages on the server side, if you receive requests that are sent to your application port number, this bind will make sure that not only you will go to the right application, but you will go to the right process within that application. So this bind really links your port number to the new buffer you created. Then we need to use this. So we do this on both sides, the client and the server side. This is a common process. And then on the client side, who's the one who wants to send something to the server, you will use the send-to function. So you will see this in the lab because you will need to write such scripts using these functions. And this send-to function takes as input the IP address of the destination, the port number of the destination, and the message to send. So once you send this, on the server side, this receive from function will block anything in the process until it receives a message from the client, and it will store the IP address of the source so that it knows whom to send back information. For instance, if the client was requesting something. And something at the end, the server doesn't have to do anything, but at the end of all, because the server can just wait and listen for new incoming requests from other clients, while the client on his side needs to close the connection. So this is what happens for UDP. It's quite simple. This is a diagram of how everything looks like. So we have the program. You're trying to write the process such that the program can talk to the server. So you create a socket, which will be typically this, and it will be linked to the buffer, and in which you can store information. And this buffer is then linked to the local port number via the bind function. And so when you receive information, it will go to the IP address, the port number of the correct application, stored in the buffer, and via the socket will go to the program such that you can read the received messages or send if it's on the reverse side. So now let's see how it is done for TCP. So in TCP it's a little bit more complicated because so on both sides we still need to use the socket function and the bind function, but now we connect completely a client to a server. Before in UDP, the server was just listening and waiting for clients to arrive. It's still the case because this is the definition of a server. Still the case for TCP. But in TCP, we really create a handshake. So when the client wants to communicate with the server, he will initiate a connection. The server will accept it, and they will be OK to communicate together. Whereas with UDP, if you send, you're not 100% sure that it will be well received, that on the server side he's waiting for incoming things from you. Here, you initiate this communication. So it's done via the connect function on the client side. So the listen function on the server side will just listen for incoming packets. It will put them in a queue. So every client that sends message will send their message, and the server will just store them in a queue and then decide, OK, I will accept this one or this one. And each time he accepts one, it initiates something different. So typically, it will create a new socket for every incoming client. Is everything fine, Tom?
I'm not sure. I guess someone touched it last week.
OK, well, worst case, it's fine. OK. So once you accept the communication, it creates a new socket, a new buffer for that particular client. And during the connect, this handshake phase, the client will send some a message that will be used to synchronize both ends such that they use the same process. If the server is OK, he will send back an acknowledgement. And then the client will send again a second acknowledgement to say that, OK, let's start communicating now. And now this time, when the client sends data to the server, he just sends the data. He does not have to precise the IP address of the destination or the port number because all this was already agreed in the connection phase. And on the server side, he will accept to receive from that particular IP address. So it's really a connection binding this particular client with the server. When all the data is sent and received on both sides, you then need to close the communication on both sides. Whereas with UDP, the server typically does not close the connection. So now on both sides, you need to close the connection. It's important to start to let the server listen before the client tries to connect, because otherwise he will try to connect in the void. But so when you do the lab, for instance, on Friday, you will need to make sure that you launch the server program before you launch the client program. But for closing the connection, it can be initiated by any side. In the end, you need to do it on both sides, but it can be initiated on both sides. So in the diagram point of view, it looks like this. It's very similar to before. We have the IP address, which is linked to the port number. This buffer corresponds to the queue of incoming messages from different clients. And each time a connection is accepted on the server side, he will open a new buffer for each one of them connected to a socket, and it will be able to talk to the application. Notice that everything is linked to one IPv4 address. So it works the same with IPv6, but it will be separated. So the program will typically know if everything comes from IPv4 or IPv6. Typically, when you write this code, the function will be slightly different name, whether you use IPv4 or IPv6. So you need to be precise this when you write when you do socket programming. But you will see all this in the lab. So now let's have a look at the basic operations of TCP. So because I said that TCP was reliable, unlike UDP. So it makes sure it handles data loss. So how does it do so? Typically, when you send a message, for instance, the first red arrow sends bytes from 8001 to 8501. And an acknowledgement, 101, which should be an acknowledgement of a previously received packet from B, and a window size, which means that this is how much he can tolerate to send at a time. but we will focus on this window size later. For now, what's important is how many bytes do you deliver, and how do you acknowledge this. So once B received this first packet, he sends some data because he needs to send back data, but he also acknowledges that he received everything until byte 8501. So when A receives the second message, he knows that B has received properly the first message. Now let's say that A sends back more data, but this next message was lost. And he, in the process, sends even different segments at a time, because we saw with packet switching, we can send several packets of the same parts of the same big message at the same time. So let's say he sends several packets, independent packets, but one of them gets lost. So when B receives this packet, for instance, he sees that in the number of bytes, something's missing. So he will send back the acknowledgement of the last previously received message, so the same acknowledgement as before. When he receives this third packet, he sees that still this one is missing, so probably A does not understand that he needs to retransmit that lost packet. So he will send again an acknowledgement for this first packet. And once A received 3 duplicate acknowledgements, so this number can be different depending on the process that uses TCP, but typically it's 3 duplicate ACKs, it will know that something's wrong and it will resubmit this lost packet. And from there, once it received the lost packet, B is able to acknowledge that, okay, he received this, but he also received these before. So he can send back the valid ACK. So this is one of the way of noticing that something's lost, and A will know that he has to retransmit something. But there is also a second way, is that each time A sends a message, he will set a timer, in which time he expects to receive an acknowledgement for this packet. If the timer is if there is a timeout and A does not receive the acknowledgement for that packet, he knows something's wrong, and probably really bad. So, because that means that in this time he also probably did not receive the duplicate ACK, so probably he lost the channel with the server. And he will typically cancel everything and restart resubmitting a lot of packets. So this is how we ensure reliability in TCP. So let's have a look at a few different names. So you will see this in the slide once you print them at home. Typically, the server program is a program that is just listening at every time until it receives connections. So it expects to receive connection requests from client, whereas the client program does not expect to receive anything unless he initiated the communication. So he's the one who's going to request data and probably receive something back from the server, but only if he requested it. So typically he will not be listening for incoming messages. So one question. Let's say that a source S sends a message to destination D of size 2000 bytes. And now this destination will perform only a single call to the function receive from. So remember that sometimes you can receive several packets for the entire message. Sometimes it's sent only in one datagram. So what do you think is true? If he calls only this function once, will the destination receive 2000 bytes only if it uses TCP, UDP, or in both cases? So I give you a few minutes to think about it. Maybe not minutes, seconds. Think about it. Okay, who thinks it's answer 1? So TCP. Okay, who thinks it's answer 2? UDP? Correct. So it's the case with us. Someone thought it was question 3? Sorry. Okay. So it turns out it's answer 2 because with UDP we send a datagram, we send the whole message. So either the destination does not receive anything or it receives the entire 2000 bytes. But with TCP we send segmented stream of bytes, and so it may be that we need to call this function many times until we are able to reconstruct the overall message. Okay, that's it about the programmer's view of the transport layer, and we will talk more about this in the lab, as I said. But now we will focus on the performance aspects of communication. How fast can we do everything? So a particular term that is very useful to talk about this is the bit rate. The bit rate is the number of bits that we can transmit per time unit. Typically, if we have a channel, so you are somewhere in the world, let's say I'm here, and I want to send messages, so I need to put all of my message in the channel. And this bit rate is the speed at which you can put messages in the channel. Then later, the message, once it's in the channel, he will need to go propagate to another place in the world where you're sending your message. But this bit rate is really about how fast can you send the message, like put it in the channel? How fast can you give it to the postman, basically? So typically we talk about, we measure this in bits per second or bytes per second or kilobits per second. It depends on the size of on the speed that you have. Oftentimes it is confused with the word bandwidth because it's typically proportional. But the bandwidth is just the width of the frequency range that you can use over that channel. And in some research areas, they focus on how to achieve the best bit rate with a certain bandwidth allowed on a channel. So this is typically a formula which relates the maximum capacity. So this is the maximum speed at which you can transmit data on a link, if everything is fine and there is no noise, for instance. And this is the bandwidth. This is the signal-to-noise ratio. You don't need to remember this formula by heart, but it's just for you to see that there are some formulas for this. Yeah, and these are typical numbers for different bit rates for different applications. So the difference between the bit rate and the transmission time is, so the bit rate is the speed that you have. For instance, how fast can you go, the maximum speed that you can use. But the transmission time is how much time you need for your own message of a certain size to be sent with that speed. So it's the time to send a certain number of bits at a given bit rate. So what is the transmission time, do you think, to send 1 megabyte of data at 10 kilobits per second? Again, I give you a bit of time to think about this. Be careful because the message is in bytes, whereas the speed is in bits. Okay, are you ready? Who thinks it's answer 1? Okay, a very large majority. I think everyone answered answer 1 actually. Does someone think it's another answer? No. Okay, so this is very clear, I guess. We don't need to go through the whole solution again. So now the propagation. So it's another type of time that we need to assess. So I said there is the bit rate, which is the speed at which you can send data. There is the transmission time, which is at how much time you need to send your particular data at that speed, at that bit rate. And then there is the propagation time, which is how much time it takes to go physically from your computer to the other end of the world to another computer. How much time it needs to propagate over a certain distance. So in this diagram, we have time on the horizontal axis and space on the vertical axis. So the formal definition is that the propagation time is the time for the head of the signal to travel from A to B. Typically, this is the transmission time on the horizontal axis, and like this, you have the propagation time. The transmission time really depends on the speed of the bit rate that you have, whereas the propagation time is quite fixed because it depends on the material you use for the channel. If you use copper cables, for instance, this is the speed you can achieve. If you use glass, this is the speed that you can achieve. And it really cannot change because it's due to the maximum speed of light that we have. So now remembering that in copper the speed is 2.3 times 10 to the power 8 meters per second. Meters? Yes, meters per second. What do you think is the propagation time around the Earth? I give you a bit of time. So this is the speed in copper cables. Who thinks it's answer 1? 2? It was too hard for you? Okay. Does someone have an answer? No. Okay. So the propagation time is the distance divided by the speed. Maybe you were lacking some input for the size of the Earth and everything. But anyway, this is the formula that you typically use. So the answer was 200 milliseconds. So these are typical times that it takes, typical transmission or versus propagation time that it would take to go from a certain distance at a given speed. So really there is some kind of a trade-off. Sometimes the propagation time will be bigger, sometimes the transmission time will be bigger. It depends on the distance and the bit rate at which you can put things in the channel. And in TCP, we need to be able to do something reliable for all of these possible scenarios. Another useful word that we're going to use is throughput. The throughput is the number of useful bits of data that are sent per time unit. So it's very close to the bit rate, except that it really is only about the useful data, the message that you wanted to send. Because if you recall what we said last week, there is every packet is sent with a header. In the case of TCP, for instance, we have reliability, so we also send back acknowledgement packets, and this is not very useful bits. So throughput is about how much data that you wanted to send originally, are you able to send at what speed. So typically in UDP, if you want to send one Ethernet packet, you need to send, of size 1, you need to send actually 53 bytes. So in the end, you don't send 53 bytes of useful data, but only one for every 53 bytes. And so at a given speed of 64 kilobytes per second, the maximum throughput you get is only 1.2 kilobits per second. Sorry, the speed rate was kilobits per second. So this is because of overheads, but you also have the protocol waiting times because of the acknowledgements, or when everything is blocked until a certain message is received. So this introduces a lot of delays. Typically, there is this protocol, the stop and go protocol, which is not which does not achieve the best possible throughput. We will see why. So this is a very simple protocol in which A sends packets to B, and B sends back acknowledgements to A for his received packets, and A does not send anything else to B until it received an acknowledgement. So here everything goes fine, but A is not sending packet 2 because he did not receive the first acknowledgement. Once he does, he tries to send packet 2, but there is a timeout because he did not receive the acknowledgement for packet 2, so he knows he needs to send it again. So in this case of protocol, we have a lot of latency typically. So let's have a look at the overall time it takes to send one useful message. So the first useful message is packet 1, and it takes time to travel to B and to be accepted by B, read by B, and then B needs to send back acknowledgement packet. And we saw here that there was some kind of a timeout here, which informed A that it needed to send this packet again. So this timeout needs to be larger than at least the round trip time. So the time it takes for one packet to go to A and from one packet to go from A to B and one to go from B to A. So the first part of the time that this whole cycle takes is the transmission time. So the size of the first packet, L, divided by the bit rate, B. This is the time it takes to put this first packet in the channel. Then we have the propagation time, so the time it takes to go from A to B, which we can say is big D, the propagation delay. And then we have the time it takes to send the acknowledgement in the channel, so the size of this new acknowledgement packet, L prime, divided by the bit rate B. And the second propagation delay, so it's D again, because we sometimes assume that it takes the same time to travel from A to B than it takes from B to A, which is not always true, but we always assume it is for modeling. So if we aggregate all of this together, the whole cycle time, it was T, the transmission time of the first packet, 2D, so the round trip time, and T prime, the time it took to transmit the acknowledgement. And in all of this time, the useful bits that were sent is only capital L. So if the throughput would be capital L, this useful bits, divided by the whole cycle time that it took. And if we rewrite this using the bit rates and all of these linking formulas, we get typically this form of the throughput, where this L prime over L corresponds to the overhead, and this corresponds to the bandwidth delay product. So the bandwidth delay product is a useful index which shows you how many bits are on the fly, how many are in the channel already propagating from one place to another, and that you cannot stop, you cannot do anything about it. And this typically shows the latency in the channel. So again, we can have the same type of numbers as previously and introduce the bandwidth delay product. And we see that sometimes the throughput is great, it's quite good, but the throughput of 3.8% in that scenario is very, very low. So because the higher the bandwidth delay product is, the lower the efficiency is. And typically, this type of protocol can be useful and can be used if the bit rate is quite small. Because if it's small, it already takes a lot of time to send data. And so if the propagation time, if the latency of the channel is quite big, we will not really notice it because it already takes so much time to transmit the data. But if you have higher bit rates, then you need to use smarter protocols. So in TCP, we use smarter schemes than this. This is an example of something quite funny. In South Africa, people were complaining about the bad transmission time, that the bad connection they had to send data over their internet provider. So what they did is that they gave a chip to a pigeon and sent the pigeon to travel 80 kilometers. And at the same time, in parallel, they tried to do the same thing by sending the data that was on the chip given to the pigeon via communication, email. Turns out that the pigeon was much faster than the internet provider. because it took for the pigeon to go there and then the download to happen of all the files from the chip to the computer. This took 2 hours and 6 minutes. And in that time, the internet provider had only achieved 4% of the transfer. This is a typically, so yeah, people were complaining about this and it hit the news. Okay, another reason why we can have a lot of latency in the network is because of congestion. We are not alone in the internet. We are not the only one who want to transmit information. So there is a certain mechanism called congestion control, which will try to attribute fairly the channel to everyone. So let's look at an easy toy example. In this example, we have 2 sources, the blue computers, and 2 servers. And in the middle, we have 2 routers. And the thickness of the links depends on the maximum capacity you can achieve on these links, so like the bit rate. In this protocol, we assume that the network can lose packets, and we assume that the sources are greedy, so they will try to send as much as possible. So they will try to send at the maximum capacity of the first link that they are connected to. In this example, S1 wants to send information to D1 and S2 to D2. So let's have a look at what happens. S1 will send data to D1 and S2 to D2. So first they will both send on these links and they will arrive at this router. Since they are greedy, they are trying to send at the maximum capacity they can afford. So S1 will send at 100 kilobits per second and S2 at 1000 kilobits per second. So in the routers, typically there are buffers if they cannot transmit all the data at once. But let's just say here that the buffers overflow very quickly and we have losses. This third link has a capacity of 110 kilobits per second. But before entering this link, we have data coming at 1100 kilobits per second if we add the 2 links. And this link is able to accommodate only 10% of the arrival of the arriving messages. So it will lose 90% of the incoming messages here. So let's say that this link has 10% of the sent messages. So if everything is done in a fair manner, we can say that it's 10% of the messages coming from S1 and 10% of the incoming messages from S2. So here, among these 110 kilobits, we have 10 that come from S1 and 100 that come from S2. It enters in this router, and now the 10 kilobits that came from S1 want to go to D1, and it has no issues in doing so because the capacity of this link is much higher, so everything can be sent. But all the data coming from S2, so by now 100 kilobits per second, want to enter this link, which has a maximum capacity of 10 kilobits per second. So again, it will lose a lot of data. So what would you say is the rate of S1 to D1? I kind of answered this question. Who thinks it's answer 1? Okay, good. Who thinks it's answer 2 and 3? Okay, so the people that answered are following. So the rate that S1 achieves is 10 kilobits per second because of all the data loss that happen here. Okay, and the bit rate that is achievable by S2 was also 10 kilobits per second because of this third link, right? So the maximum throughput that we have here is 20 kilobits per second in this network. So this is because they are greedy. Okay, I just want to see something. Okay, this is because they are greedy, but we can think of another way of handling this fairness problem. If we had a larger view of the network, so at first, in our previous example, S1 and S2 were sending at the maximum capacity they could afford on their first link. But now, if we think that they could have a larger overview of everything, and that they would send at the maximum capacity of their weakest link, so for S2, even if he's alone in the whole network, he will never be able to achieve more than 10 kilobits per second, because this is the maximum capacity on this link. So if S2 would send only at 10 kilobits per second from the beginning, and S at 100 kilobits per second, then S1 would be able to achieve 100 kilobits per second of throughput, of bitrate, because he's able to send everything he wanted to send. All of the losses were due to S2 being greedy. So typically in TCP we try to achieve such fairness in networks. So in this previous, yes?
I just have a question. In order to do so, S2 has to know the bitrate of D2, right?
Yes. So he does not. So he would need to know this, the bitrate of this link. Typically, what happens in TCP is that they don't have the overall picture. They don't know who wants to send to what and what is the capacity. But what they do is that they increase the rate at which they are sending. They go slowly. They increase linearly, and each time they have a positive feedback, a positive acknowledgement, they will continue increasing linearly their bitrate. But as soon as they have a negative feedback, so a packet loss or something like this, they will reduce this bitrate by half. So typically we say that it's an additive increase because it's linearly, but multiplicative decrease because it's directly divided by 2. So this is how they handle this, and it was shown that if all sources try to apply this and have the same well, in certain assumptions, which I don't want to go into details now, they can achieve a very good fairness in the end. So in this example, we have a feed-forward network. So the dependency between the sources and the routers is all linear. In this other example, we have a cycle dependencies. So in this example, we have a network where all the blue nodes correspond to routers. And at every node, we have a source sending data. So at this node, we have a source sending data, and it will go 2 hops away before going to the destination. This is the case at every node. So we have this one, which is shown here, but we also have this one, and so on and so forth. So no messages will be stuck in a loop because they only go 2 hops away, but all of the messages sent by I, the bit rate used by I will impact the one on this link too, and so it will have to be summed up in some way with the messages sent by source I plus 1. So whatever source I does impacts source I plus 1, and source I minus 1 impacts source I. So now let's have a look at how much can source I send to the destination. So we have lambda primes, and lambda second here, which corresponds to the bit rate. Lambda is the bit rate at which every source sends data. They all have the same rate. Lambda prime is the bit rate that source I can achieve on this link, and lambda second on the second link, and the output corresponds to this lambda second. So now we assume that this is the case at every node, okay? And we want to know, depending on lambda, how much can lambda second be? How big can lambda second be? And this depends on the link between lambda and the link capacity. Because on every link, we will have 2 sources of messages. On this link, for instance, we have messages coming from source I and messages coming from source I minus 1. So if this common lambda, which is the same at both nodes, is smaller than half the capacity, then everything can work fine and there will be no losses, right? So in this case, if lambda is smaller than the capacity of the link divided by 2, everything is fine, and lambda second is equal to lambda, so everything that was sent should be able to be received. Now in the case, is everything clear from this? Yes. So now in the case where lambda, the initial bit rate, is larger than this capacity divided by 2, we will have losses. So let's have a look at how we can analyze this. So when lambda arrives here, this capacity here is able to accommodate only a certain amount. So it will be able to accommodate, it will receive lambda plus lambda prime, because on source -1 we sent something, and on this link we had lambda prime. Plus lambda will arrive here. And the maximum capacity is C. So the ratio of the accepted data is C divided by lambda plus lambda prime. So we can say that this lambda prime is equal to this ratio times the incoming lambda, the incoming bit rate. So this is why we have this first formula. And then we can apply the same thing for the second link. Lambda second will be the same ratio, but applied to lambda prime, the previous link. And so now we have two equations with two unknowns, lambda prime and lambda second, because lambda is given as the initial bit rate. And so we can solve the first equation to find lambda prime, and then use this to solve the second equation and find lambda second. So if we rewrite everything, we can rewrite lambda second as a function of lambda as such. So if lambda is greater than the capacity over 2, this is what lambda second is equal to. And if so, we tried to plot this lambda second as a function of lambda, and we see that, so this is lambda here, so the initial bit rate at which we send, and this is lambda second, so the bit rate at which we can receive, and the receiving bit rate grows until we reach this threshold of C over 2, okay, and then if we go above that, it will decrease. It will really decrease, and if we use Taylor expansions, we can see that lambda second is actually in 1 over lambda. So as lambda grows to infinity, lambda second goes to 0. So it will really go to 0, and this is what we call congestion collapse. So in this case, not only it is bad to send too much data, but it gets worse and worse, and at some point it's so congested that we will not be able to send anything at all. So, okay. So the take-home message is that we need to think of smart ways of handling congestion, typically the way of TCP, not using stop-and-go protocol, to handle this in a smart manner. So the way we do it is exactly how I explained it to you earlier, with the window size and linear increase and multiplicative decrease of how much we allow ourselves to send. Okay, so if I can say it again. So it will start slowly to send data, and as if he receives positive acknowledgement, he will increase linearly this window size, so this bit rate. And if it receives a negative feedback, so a packet loss, it will divide by 2 the bit rate. So this is used in the internet, and it's very useful, but UDP sources typically don't do this, and it's a threat to the internet. So in the future, we expect that these UDP sources should try to imitate TCP in that aspect. Yeah, and I think I've said everything I wanted to say, except that in smart grids, we use more than this. We use traffic engineering to isolate critical flows, because we can have a larger overview of the network, and we can protect it such that we achieve the best bit rates possible. Anyway, and most of the time, you are asked to look at what happens via Wireshark. This Wireshark is like a spying software that allows you to see what messages are sent and what messages are received at particular interfaces. So you noticed different messages with different protocol type. The protocol is really the name of the process that allows the communication between two entities. And I noticed that some of you got mixed up between what is a DNS server, but the protocol, and everything was a bit mixed in their head. So let's try to have a view again. So for instance, let's take an example where we on our computer, like in the lab, we are trying to ping Google, okay? And at first we are just one computer in a room and we don't really know how to access to Google. So we just have the Google name. We don't have the IP address of Google. The first thing that's going to happen is that, okay, you have your computer and your computer has a MAC address. That MAC address was given to the computer by the person that constructed your computer, okay? So with this MAC address, he's going to do some kind of a protocol such that he can understand who is around him. So what are the MAC addresses of the people around him? Okay, their unique name, that's the one that they will have all the time. So this is why you saw on Wireshark some ARP messages, okay? So it's going to be ugly, but I'm going to write things. So you have the MAC address that you have initially there, okay? Then you will do ARP protocol to get the MAC of others in the LAN. Okay? Once you have this, you are able to physically send messages from one place to another. Although we still need to use IP, and typically when you opened your computer and you looked at the networks, you saw that there were different possibilities. And I asked you to disable IPv6 to first focus only on IPv4. And at that point, you saw that you have, using some commands, you were able to see that you have an IPv4 address. And this was actually attributed to you via a certain protocol that we will not see in this course. But your computer was attributed this IP address that he can use. And so, IP address, you didn't really have to think about this. And then he also has the networked mask, so he knows who is in the same LAN as him. Okay. Net mask. It's not that he knows who is, but he knows that everyone with an IP address that starts with the same start as his own IP address is in the same LAN. And these are the people that he needs the MAC address from also. Okay. So this is the net mask, and then you notice that he also got a gateway. And the gateway is the first router. So if you are in a LAN, you have your computers, you have a phone, you have a printer, and maybe a switch or Ethernet box or something like this. But you also have a router which will enable you to go further away than your LAN. And this router, you had an IP address for this router. This router is what we call the gateway because it will allow you, it's the gate to outside of the LAN. So now on your computer, at first, without you doing anything, okay, you had a MAC address. It managed to get an IP address, which is logical corresponding to where you are in the world. It has a net mask, so he knows which IP address corresponds to the ones in the LAN, and a gateway, so he knows who to contact first if he wants to send messages outside of the LAN. Now, the overall aim was to ping Google. So what happened is that first he sent the ARP messages, which I just talked about, to get the MAC of the others in the LAN. And then he uses this to contact the DNS server. So the second message you saw was DNS request and DNS response. So this DNS, okay, sorry, never mind. I hope what I'm saying is enough. So he will try to contact the DNS server Okay? And what happens for this is that the DNS server has an IP address. Okay? So he will contact the IP address of this DNS server. And this IP address was given to him already initially. So he knows who to contact the DNS server. But to do this, the DNS server is usually not in the LAN where you're in, so he will need to go through the gateway, through the first router, okay? I still want to write because... So the first time we have some kind of message like this with so many segments is when we will contact the DNS server. So let's have a look. Okay, we have our computer here. The router, which is in your LAN but allows you to go outside of the LAN, and the DNS server. This is the first important message that is sent. The computer is contacting the DNS server to find out the IP address of Google. So in the message here, you have IP destination address, which is IP DNS, because the end-to-end principle of IP says that you send the source address is your own and the destination is only the last person you want to talk to, like the person you're aiming for. So IP source is IP of the computer. And then to do this, first it needs to go through the MAC, through the router, which is your gateway. So the MAC destination at this point will be the MAC of the router, and the MAC source will be the MAC of the computer. And this is in the header of your message, okay, which allows you to send. But then the payload contains who is google.com. This is in your DNS query that you will see on your computer. You're trying to reach the DNS server, but first you need to go through the gateway. So the end-to-end principle of IP says, I want to reach that person, but physically, the first hop you need to first go through, so you need to change the MAC addresses, is the one of the router. Now the router receives this message. And he sees, okay, the MAC destination address is my own, so clearly I have to do something with that. But the IP destination is not my own, it's the one of the DNS. So it means I need to forward it to the DNS. And so he will forward this message where the IP destination and source will not change. So it's still IP DNS and IP computer for the source. Okay, this does not change. But now, the next hop, assuming that we don't need to go through other routers to reach the DNS server, the next hop will be the one of the DNS, and the MAC source will become the MAC of OR. Okay? And it contains the same message, who is Google. So this is assuming that we need to go through only one router, the gateway that is in your LAN and allows you to go further. But it's possible that the DNS server is even further away and needs to go through several routers, in which case you will go from router to router by changing only the MAC destination and source addresses from hop to hop. The traceroute command allowed you to see which one were these routers on the way. Okay? Now, the DNS server receives this message. He sees the destination address, MAC address is his own, and he sees the IP destination address is his own too. So he does not have to forward it, but he actually has to read what is inside. What's inside is asking who is Google. And the DNS server is built in such a way that he has a lookup table and he can find out the IP address of Google. So now he will send back a message to the computer. This pen is terrible. To the computer via the router again. So now I'm still going to write it down, even though it's slow, but that way I'm sure you see everything. So now the IP destination becomes the IP of the computer. The IP source becomes the IP of the DNS. The MAC destination is the MAC of the router. And the MAC source is the MAC of the DNS. This is in the header, and in the payload we will have Google is, let's say, something 8.8.8.8. Okay, it's something else, but let's assume it's this. Now the router sees this incoming message. He sees the MAC destination address is his own. He needs to do something with it. He sees the IP destination is not his own, so he's not the endpoint. He needs to forward it to the computer. So he will change the MAC addresses in the header, but not the IP addresses. So the IP destination will be the IP of the computer. The IP source will be the IP of the DNS. This has not changed. The MAC destination is the MAC of the computer, and the MAC source is the MAC of the router. Okay? And it contains the same payload, 8.8.8.8 equal Google. Okay. Now this was the DNS request, and this is the DNS request that you can see on Wireshark, because at Wireshark you sit exactly here on your computer. So you don't see all of this. You would see it if you use Wireshark at the router or Wireshark at the DNS server. But from here you see this as the DNS request and this as the DNS answer, response. By now, your computer has understood what is the IP address of Google, and he can, because he has done the ARP first to recover the MAC address of the router. This was the important part. And then, so he knows what to put here. And then he did the DNS, so now he has this IP address of Google. Okay? And now he is physically able to actually ping Google. So what happens is that he's going to replace all of this. So let me go here. So with all of this information, the computer will reach the Google server by going through the gateway, the router. And most likely there will be several routers after the LAN, but for simplicity, let's do it like this. Once again, the ping request will be with IP destination, IP of Google, IP source, IP of the computer, MAC destination, the MAC of the router. So it's the same MAC destination address as in the DNS request, because it's always the same gateway. MAC source, MAC computer. And now it has ping. It's just a request to ping, just to know if the Google server is alive. The router will read this. He will see he has to do something because the MAC destination address is his own, but the IP destination address is not his own, it's the Google IP address. So he will change the header without modifying the IP source and destination addresses, but only the MAC addresses, so that we can go to the next hop until it eventually reaches the Google server. So what happened, the way the router, in this simple scenario, it feels like router has an input interface and output interface. But the router, in fact, has several interfaces. So to know which MAC destination address to put here, to know on which interface to send it, who is the next hop, he will use his MAC routing table that we saw in the class last week. And he will use the routing table and the longest prefix match. So if he receives, okay, the IP destination address I'm trying to forward to is 8.8.8.8, he has a routing table and he will look for the longest prefix rule in his table to know, okay, I need to send on interface 2, for instance, to MAC destination MAC of router 2, okay, if there was a router. Is it clear? Yes. Now, the other important thing I mentioned last week is this end-to-end principle. So in the end-to-end principle, what I mean is that in the header, the intermediate systems, so the one between the source and the final destination, they never modify this IP destination and source address. They only modify the MAC, which allows you to go from hop to hop. But last week we saw some examples of proxies, application linear gateway, mail server, all of this, which changes that. And they do not respect this. And in this case, this type of intermediate system will change the IP destination and source. So that means they end the TCP connection and open a new one. So in the case of the email, let's say the company gateway, the company proxy, for instance, we had a company that did not allow you to go to YouTube videos, for instance. So typically what would happen if you're on your computer, you would send, okay, the gateway that would be in your computer would be the gateway, would be this proxy that will filter out the request. So this will be sent to the proxy, and the proxy will not respect this rule of end-to-end principle. He will look at the IP destination that was asked and say, okay, I don't want to forward this because this is not at all allowed by the company rules, and he will just drop the packet. But in theory, if we respect this end-to-end principle like we try to do as much as possible, the router does not even look inside at what is the content of the message, but just changes these MAC addresses. Okay? Yes?
It's a security to do this, to close the TCP.
Yes, it can have different, it can be for different reasons. We saw last week that it can be for security, or it can be just for company rules, you know, like they don't want you to have fun on YouTube, you're supposed to work. It can be also for performance, because these special routers can cache also information. So if you request something that has been requested a lot in the company, instead of requesting it to the server, he will directly send you what he has cached in memory. It can be for mobility, for the email case, where you cannot send directly to the person directly, but because the person is not always physically looking on his phone or computer at his emails, but you send to the server, email server, who will then send it to you once you request to read your emails. So we have different possibilities in which this is useful. Yes?
To come back to the DNS, can we consider it just like some kind of library where all the IP addresses are, and whenever you need to know one IP address?
Yes, and typically you will see that they can link. So there are names like Google that are linked to IP addresses. Google may have several IP addresses, so he will send back one to the requester, and Google may have an IPv4 and an IPv6 address. So typically when you ask for this, you ask for either the IPv4 or the IPv6 address, and then the DNS knows which one to send to you. Any other questions? Please feel free to ask, because really if something's unclear. Yes?
I think I asked you this last Monday, but I don't remember. How does the computer know the IP address of the DNS server? Is it set by default?
It's not really set by default, because if you move in the world, it will change. Yeah. But it is set via this protocol that we're not going to go into details now, that also allows you to have an IP address and to know who is your gateway and to know the net mask and all this. There is some kind of a protocol that happens before, so that the computer is able to localize himself in the world and has all the necessary information such that for you it looks like it's just plug and play.
It is related to what you had told me, that when you enter a place, you obtain some IP address that is set automatically.
Yes.
By
so this can be done automatically, but you can override it if you want to do it manually. If you want to access to a particular DNS server, for instance, Google has a DNS server. If you can know its IP address. Actually, I think it's 8.8.8.8, if I'm not wrong. This is the DNS server of Google, and if you enter it manually in your computer, it will work fine. But instead of going to the closest DNS server that will automatically be attributed to you, it will go to this other DNS server that you're asking for. It's also possible. Just like you can also decide on your own IP address by yourself. But in terms of collisions, it's risky. So we usually don't do this. Usually we just use the automatic way of doing it.
There are some restrictions. For example, you cannot set your IP address the same as Google's, for example.
Yeah, of course, it will not work. Yeah. That's why if you want something that works, usually you just use the automatic protocol. Any other questions? No? Everything is clear? Why not?
Well, specifically on questions, I would ask things, but like in terms of this, I mean, it's fine. But can I ask, so when I'm accessing the lab's webpage, so I see the DNS, the IP address, and the IP address of the lab, but there are also like other things, like other TCP, other IP addresses. Like how?
You mean in Wireshark?
Yeah.
Yeah. So it's possible that there are a lot of other things, especially if your, I don't know, email is open, or if you have Spotify open on your computer and other things. And also it's possible that this automatic scheme re-updates very frequently. So there will be more app requests frequently to know if someone else came in the LAN. It auto-updates a lot. So this can also explain why you see these messages. Also, your OS tries to update itself, so to update the apps that you have. So you can see a lot of requests. Actually, it's very interesting because you see a lot of behind the scenes that you don't know about, but that constantly happen between your computer and the servers.
But every time when we access like a web page or something, this is what, I mean, the end-to-end like DNS, and then web pages like.
Yes. Yes, this is what you're supposed to see. Yes.